I can now move to Rosalba Pacelli. Rosalba Pacelli is a postdoctoral researcher at Istituto Nazionale di Fisica Nucleare in Padova, and she got her PhD in physics from Politecnico di Torino in 2024, and before she was at University of Milano and also I believe at University La Sapienza in Rome. She is working on the relationship between the learning in artificial neural network and statistical physics, and her seminar today is about deep neural networks and the proportional regime, a statistical mechanic approach.
Thank you. Thank you for the introduction and of course for inviting me. Let me share the screen. Okay. Oh. Okay, can you see?
Yes, we can see. We can see the screen, please.
Okay, so today, as anticipated, I wanted to talk about a statistical mechanics framework for studying deep neural networks in the so-called proportional thermodynamic regime. I was told to be pedagogical, so I decided to start from my favorite definition of deep learning, which is just a new paradigm of coding. You can think of it like this. So in classical coding, the coder knows the desired output of the code, and so they write it line by line in a deterministic way, and they are sure in the end, if they are good coders, that to a certain input a desired output will correspond. In deep learning, the situation is different. The desired output is known, like the classical coding case. Also, the desired input-output map, in a sense, is known, but the coder gives the computer some data rather than lines of code, and then the algorithm, the machine, in a way learns the code by itself. So the interaction between the coder and the machine is through data. So for this reason, as was classical coding decades ago, deep learning has been used by scientists in many fields to advance their understanding of the science in biology, neuroscience, physics, social sciences, and many others. And this is, I think, the most popular way of using deep learning in other fields. What I do is the other way around. So rather than applying deep learning to my field, I apply my field to deep learning and in particular to neural networks, which are the main characters of deep learning, to understand it. Of course, it's not only the physicists, also this can be done with mathematics and statistics tools. Why would someone do that? Because machine learning and neural networks achieve amazing performances in some kinds of tasks. For example, in computer vision or in some games like chess and Go, they achieve superhuman performances. And recently, we have seen that thanks to neural networks, we have conversational agent chatbots, which do a lot of the boring stuff for us, like DeepSeek and ChatGPT. But nonetheless, we lack a comprehensive theoretical framework to grasp and describe and most importantly explain these performances. We face a lot of conceptual open problems. So let me delve into some details and present the ingredients for a general framework of deep learning. We have the deep neural network. Here I sketched a fully connected model, which just means that all the neurons, these bolts are neurons, of one layer are connected to all the neurons in the layer above. So you have to imagine the deep neural network as a non-parametric function approximator, sorry, a parametric function approximator parameterized by the weights theta. And in particular, the most popular models, I would say, most used models until recently at least, because the transformers is, for example, different, alternate two kinds of operations, an affine operation and a nonlinear operation. The network input is an n0 dimensional vector, and the output, in this case, is a scalar, but can be, of course, in general, a d-dimensional vector. The second, I will call the collection of the parameters of the network as theta. And I will mean all the weights of the various layers. The second ingredient is a labeled collection of examples. So data is crucial. Here I reported the MNIST dataset, which is a popular benchmark computer vision dataset. And in this case, the inputs are the pixel, the image as an array of pixels, and the labels are the categorical labels of the digit. The third ingredient is a loss function, an energy, which is the object that is minimized or minimized or maximized, it depends, to train the network. The minimization of the loss function will give a theta star, a set of optimal parameters that will be used to make inference, or in general, it will represent the trained model. So if one wishes to explore this kind of architecture with statistical mechanics, one can be interested, for example, in computing the posterior Gibbs distribution of the parameters after training. Of course, to do this, we also have to define a prior statistics for the parameters, so there is an extra ingredient, and the Gibbs posterior is defined in the usual way. Of course, the hardest part of this is to compute the normalization factor, that is the partition function. And more concretely, I will attempt to do so. And in general, for the rest of the talk, I will put myself in the case of means of quadratic loss function, so the mean squared error. And I will choose a Gaussian prior. Let me just point out that with these choices, compute the posterior Gibbs distribution is the same as the Bayesian posterior, with Gaussian likelihood and Gaussian prior, and the partition function is just called model evidence in this other jargon, the statistics jargon. Of course, computing the partition function is not always possible, not even with some approximation. It is possible with finite number of parameters for deep linear networks, which are exactly the same as deep neural networks, but the nonlinearity is removed and replaced with the identity function. In this case, everything can be computed exactly. In all the other cases, we need a thermodynamic limit, which means in this case to take the limit of infinite number of parameters. And of course, we need also a scaling for these parameters. And in general, one wishes to scale the weights in layer L with a negative power of the number of hidden units of neurons in the same layer. Of course, everything depends on the choice of these two, of the limit and the scaling. There are many possible ways, of course, to address to many possible choices. And historically, the first one in the 90s, this was done by Radford Neal in the 90s, is now known as the infinite width thermodynamic limit, which considers a fixed number of training examples. P is the size of the training set, and the number of hidden neurons in all the layers is taken to infinity. The scaling is chosen to be 1/2, which is what let me say the central limit theorem would suggest. So it's a very natural choice, and this combination of thermodynamic limit and parameter scaling is known as lazy training infinite width. Lazy because these models do not exhibit feature learning, which is a key characteristic of neural network, characteristic that we wish neural networks would exhibit. And when I say they do not exhibit feature learning, I mean that the prior statistics of the weight is not changed by training, and so the posterior statistic of the weight is exactly the same as the prior. Later, another choice was made by, I think, originally Montanari, which is thermodynamically the infinite width limit. So a fixed number of training examples and a growing number of hidden units in the hidden layers. But the scaling, the gamma is chosen to be 1. This is known as mean field infinite width. And in this regime, there is a feature learning phase. So the posterior is affected by training. But for the sake of this story, I want to choose a third way, which is the proportional thermodynamic limit, which is the limit where both the size of the training set and the number of hidden neurons go to infinity at the same rate, so with a ratio that is finite and fixed. And the scaling in this case is the same as the what is called standard scaling, so the same as the lazy training infinite width. For this, the nice con of this choice of the proportional limit is that this allows to test prediction on finite networks, because results do depend on alpha, and so in a way they do depend on NL. And also, let me point out that when alpha L is taken to 0, we should recover in the proportional limit the same results as the lazy training infinite width. I have, okay, let me present some results. And I will only tell something about one hidden layer network. So L is equal to 1. That we have 2 layers of trained weights in this model. And we find that the partition function of a number of different architectures in different frameworks can be reduced from an integral which is on all the networks, the network parameters, so a huge number, and in particular this number goes to infinity. We can reduce it to an integral over a finite number of parameter or order parameters, and in a form that is suitable for saddle point integration. The quantity in the exponent is S, an effective action. It has this form that I report here, and this form, this functional form, is the same in a number of different architectures. For example, fully connected, convolutional, locally connected, with or without pooling layer. And also for transfer learning and multitask learning, we have the same functional form of the effective action. And what differentiates all these cases is this quantity, this renormalised kernel, which is a matrix. This matrix combines the order parameters and the NNGP kernel, which is the kernel that arises in the infinite width limit. Both the dimensions of the matrix Q and the particular form of the operation that combines Q and the NNGP kernel are defined by the network's topology. And so also the dimensions of the renormalized kernel are defined by the network's particular topology. For example, for fully connected networks with the output classes, Q is a matrix of a D times D matrix. So it has the dimension of the output vector, and the operation that renormalizes the kernel is the outer product between a P times P matrix, which is the NNGP kernel, and the Q matrix. Let me point out that when D is 1 equals 1, this is just a product, and so this renormalization is just a rescaling of the NNGP kernel matrix. It does not affect, for example, the eigenspectrum of the matrix. This lambda is the inverse of the prior variance of the weights. Sorry for the misprint. Okay, and for convolutional networks, the situation is different. Even when D equals 1, we have a renormalized kernel that takes the following form, which is a rotation of the NNGP kernel matrix. In this case, the NNGP kernel matrix is bigger, is P times NP squared number of entries, where NP is the number of patches. For those of you who are familiar with convolutional networks, you already know. For those of you who are not, I hope that this GIF is enough. In this case, the number of patches is 9. Okay, and this renormalization is non-trivial in the sense that it changes the eigenspectrum of the NNGP kernel matrix. So, of course, we tested our theory, as I anticipated, on finite networks. In particular, we chose to compute this observable, that is the generalization loss, which quantifies how well the network will perform on unseen data, data that was not in the training set. And of course, we have to train our networks with the discretized Langevin dynamics, because we wish to sample from the Gibbs posterior distribution. So here I'm showing the generalization loss as a function of N1, which is the size of the one hidden layer of the network, for networks with a different number of output classes. And solid lines represent predictions from the proportional width theory by explicit minimization of the effective action. The dot dashed line represents the infinite width prediction, which is independent of N1, as it should be. The dotted line represents an heuristic solution in the proportional limit, which is computationally much less costly, but is, of course, an approximation. And dots represent the results from numerical experiments. So, as you can see, we have a pretty good agreement between theory and experiments, and in particular in the random, in the case of random data, this agreement disappears for very, very small values of N1, even though our result, of course, is valid in the thermodynamic limit where N1 goes to infinity. Okay, so for my last 2 or 3 slides, I wanted to talk about the relation between this proportional width theory and Gaussian process regression. So our proportional width theory boils down in the end to minimizing the following effective action with respect to Q. This will give a value Q star that will define completely a predictive posterior distribution, and we can measure all our nice observables. But let's forget about this for a second, and let's imagine that we wanted to solve the same problem that we have. Instead of solving it with a neural network, we wanted to solve it with a Gaussian process regression. So, Gaussian process regression is a very standard inference method. So we would only need to define a kernel function, a 2-point function. Let's imagine that we were to choose the renormalized kernel as our ansatz. Of course, this is a God-given ansatz because the proportional regime does not exist for the moment, but let's imagine that we came up with this idea. What one would do in a Gaussian process regression is to fix the value of the hyperparameters by maximizing the logarithm of the model evidence, which takes this form. This, of course, this maximization would yield a value Q star, which would give the same exact predictive posterior distribution that we get in the proportional limit. But, of course, the two quantities, the log of the model evidence and effective action, are not exactly the same. They share one common piece, but the effective action has two extra terms that are enforcing really a physical constraint of positivity. This term is here because this effective action comes from a physical theory, and we know why, because we know the physical interpretation of this order parameter, which, for example, we know it in fully connected networks, where we know that Q star, which is a matrix Q star AB, is just one entry, one element of the matrix Q star. This is the average over the posterior Gibbs ensemble of the dot product between vector VA, which is purple in this figure, and VB, which is blue. And these are the weight vectors that correspond to a particular output class. So, of course, this is a covariance, and the constraint of positivity this is a covariance matrix, so this explains the constraint of positivity. In the infinite width limit, this expected value is just the delta function, the Kronecker delta. And so this correlation in the last layer vanish, as we know, and so does any feature learning in this regime. So everything is consistent, and we are very happy. And with this, I am done. I just want to summarize. I have presented a framework which is very flexible. It can be applied to many contexts and is able to capture effects of training in finite networks. Of course, our derivations are not mathematically rigorous. They rely on some approximations. For example, a Gaussian approximation of one variable at some point of the calculation. Of course, I cannot be more precise than this. And so we have yet to understand under which assumption and to which extent this can be made rigorous. So thank you for the attention.
Thank you. Thank you for the talk. Are there comments or questions? Perhaps I can. Oh, is there anyone? Oh. You said in one of your first slide that you are in a regime where you have a P and N that are proportional, and then you have this alpha parameter. Can you comment a bit more on this alpha parameter, especially if the value of alpha equals 1 might play a role or not? Because here you have that alpha must be just greater than 0.
Yes. No, it is not problematic. It's just that, of course, you don't know at which alpha your theory stops working. Mm-hmm. This is the only problem, but there is no analytical problem in any value of alpha. We get the correct result. Sorry. We have that with alpha that goes to 0, we correctly recover the pre-existing theory. So there are no issues.
Okay, thank you. There is a question, I think, in the chat asking what is the physical or statistical interpretation of the matrix order parameter Q?
This one, maybe I was too fast on the last. This one, basically, for fully connected models, the entries of this matrix are the average overlap between weight vectors of different output classes. They quantify correlations in the last layer at the saddle point. Of course, this is the value at the saddle point. Did I reply to your answer? And these correlations vanish in the infinite width limit with alpha that goes to 0.
Okay, thank you.
Okay.
And after, you see the chat, okay?
Yes. How does the renormalization where the parameter affect the learned function space of the network? I think that in general, okay, it depends on the architecture, but this solution depends explicitly on the data. So it just incorporates more information on the data set with respect to the infinite width limit. For example, for fully connected models with only one output class, it almost does not affect anything, because if this just becomes a product, then everything that Q can do, also the prior can do. So basically the feature learning that happens in fully connected networks with one output class is trivial, in the sense that you are asking that the space of learned function does not change. But for the convolutional network, it does. And we see it experimentally that the generalization error can be lowered by having learned this set of parameters. Thank you.
Mm-hmm. Any other question or comment? So if not, I think it's time to close the session. Thank you again to our speakers of today, and you are invited to join again the seminar of next month. That will be as usual in the first day of the month. Thank you very much. Bye-bye.
Thank you. Bye.